let's have a look at turbulence and wall friction. I already introduced you what is turbulence, what is the Reynolds number, how can we calculate if a flow is turbulent, and I teach you if we calculate the Reynolds number is density times velocity times acoustic length divided by viscosity. So if we have fast flows with low velocities, we get high Reynolds numbers, and that means we get turbulent flow. And I teach you flow is turbulent if the Reynolds number is higher than 2320 and it's lower. If it's lower, we have laminar flows, and so you can calculate if the flow is laminar and turbulent. And I also teach you if we have turbulence and we have friction inside the fluid, we have tensions inside the fluid, and this means we can get losses of pressure. So if you have a rough wall and turbulent flow, you will need much bigger pumps and higher pressures to use this pipe system than if you compare it with a pipe system where you have flat walls without any roughness. So here is also something about turbulence and friction. You have a closed layer, you have a boundary layer over the flow, and if the roughness is not too high and the boundary layer is big enough, bigger than the roughness, then you have a smooth wall and will have no pressure drop on the wall. But if you get higher roughness, higher sand grain roughness, and you also have a boundary layer, but the fluid will also hit the roughness. Yeah, you can explain it like this. Or if you have turbulences, high turbulences, they will go down into the valley of this roughness of the wall, and then you will get pressure drops. Okay, here's a sketch of a pipe, and there's an additional effect I try to explain with the candle. If normally the fluid flow enters the pipe, you will have a uniform velocity profile. You can also call it a plug flow profile, but in the middle you have uniform velocities, but at the side of the pipe you will have roughness always, and you will always have the velocity 0 at the wall of the pipe. And then when the fluid flows, you get more and more parabolic profiles. So this means the velocity will be more laminar. Yeah? So even when you enter the plug with a turbulent plug flow profile and you have special lengths of your pipe, after some time the fluid will be more laminar, and this will have a big effect on the fluid flow. Yeah? You will have, of course, this is an optimization of the flow, you will have less pressure drop, but on the other side you will have also less heat transfer. So it can be good to get this laminar flow if you want to have less pressure flow and a small heat transfer. But if you, for example, have a heat conductor and you want to have high heat transfer, then you have to disturb this fluid flow. Then you have to produce more turbulence, and you have to know for every fluid how high this length, this characteristic length is. It's always about 0.05 of the Reynolds number, and then for every fluid you have to disturb it from time to time again. This can be really important, for example, in food industry. If you want to heat up milk, you have to know the viscosity and the density of the milk, and you have to know your pipe system and the length after which time you have to produce turbulences again. or of course in every kind of heat conduction systems. This can be really important. And here is the formulation of the pressure drop. And formulation of the pressure drop, this is a more simple part now. It's only for smooth walls of formulation, and you have your delta P, your pressure drop, divided by density, and this should be the Chi value, a value you have to measure. You do know this value, and this value will be multiplied with velocity squared divided by 2. And if you look closely at this equation, you can also see Bernoulli's law again. If you multiply this equation with the density rho, you get a pressure drop is velocity squared divided by 2 times rho. And this again is our dynamic pressure of the formulation of Bernoulli's law. Okay, with this equation, if you have special loose numbers, you multiply them, you make a sum of all the looses over the whole pipe, and you have to sum them up, and then you can calculate your pressure drop. And now you ask me, how can I get all the Chi values for the different armatures, for the different elbows? And more or less there are two answers to this question. At first, of course, you can do a CFD simulation. You can construct your pipe system and make a computer simulation with CFD for your pipe system, and then you can calculate the pressure drop. That's the first possibility. Or if you don't have fast computers, or if you don't have so much time, you can take a table. There are big tables, like really big books. I can also give you some, if you like, I can give you some literature about this. And in these tables you can look up every different elbow or pipe system or diameter, and for all these pipes there are measured values for the pressure drops, and you can refer to this list, and then you can take the pressure drop for your elbow or your pipe system. And there are thousands of different elbows or pipes or different geometries here. Even if the angles change, you get a big list of all these Chi values, and then you can also decide on your own how the system looks like and which Chi we want to take. Okay, but of course you can imagine CFD, detailed CFD simulation is much better. It's much more realistic. Okay. But if you look back on CFD a bit, and you're also already familiar with this tool under CFX, there's always something I want to mention. Do not proceed with CFD calculations until you have generated a high quality mesh. And here again you see a so-called Cartesian mesh, an example for mesh. Of course, if you have a rough pipe and the mesh is too coarse for this roughness, or too coarse to build up a realistic mesh for the armature or for the valve, the results will be also not so realistic, of course. So that always keeps this in mind. Okay, so our aim is to measure pressure drops, and our aim is also to examine pressure drops, but it is also to visualize them. If you make a CFD calculation of an elbow, you have to be able to visualize the fluid flows. Yeah? And this visualize is somehow difficult. I showed you that I did it with ink or with an infrared camera or with computer simulation, but normally you don't really see it. And I want to mention there are much more sophisticated versions to visualize it, more sophisticated methods. For example, we did a Schlieren measurement in our labs. We have some experience with this. You can make smoke visualization. That was not successful. In our case, it's the same as with ink. It's a bit difficult, but there are also methods like particle image velocimetry or particle tracking velocimetry or laser Doppler anemometry, but it's complicated names for sophisticated methods, and you can imagine these methods can be really expensive and maybe too expensive for us to handle. Okay, here's another method to show, to visualize fluid flows and to visualize pressure drops. And we can also, okay, that's maybe a method I have not mentioned so often, but it's also big business. Ships, the wall around ships have to slide through water, and here we also have pressure drops, we have fluid flow, and to visualize the flow around the ships we can have also a sophisticated method where we use oil, and we put this oil droplets or color mixed oil, and we put it on the surface of the ship. Then if the ship flows through the water, the oil will be washed away a bit, and then we get this characteristic streamlines on the body of the ship. And here's it's a really nice comparison of this ship streamlines and the numerical simulation. And maybe if you look closely, you can see both pictures fit right good. Okay, and that's enough. And that's the last version of a visualization of fluid flows. And I take this picture really often because I like it really much. That was a snail or the volute of a steam turbine. We built it when I worked at Bosch company, and we made there was oil at the ceilings and at the gears of this turbine, and of course on the axis, and this oil wasted our fluid stream a bit, and when it gets hot at the walls we got an oil layer, and on this oil layer you can see really good, if you look close at the slides, you can see really good streamlines of the fluid flow, and you can see where you had more turbulent flows here and really low velocities, and you had here high swirls, and you can see a really big turbulent swirl at the axis of the snail. And what I did, I made a model in CFX for this snail. I made a CFD simulation for the snail, and then I placed it directly over the picture to visualize the flow inside the snail.